I hope you just watched Mr. Haas's fabulous sneak peek about related rates. We're going to dive into the last example he gave, and that was of the circular puddle. So again, as he described, related rates problems look to see how different rates of change are related to each other. So let's say we have a circular puddle, and it's perfectly circular, and we're not worrying about its depth for now. Okay, and let's say the rate of change of the area, the surface area here, is 2 square centimeters per minute. So I don't know, I've got a hose of water just dribbling in, and the area is changing at a constant rate of 2 square centimeters per minute. I think you could agree, and you can go back and look at Mr. Haas's video, that as the area is growing, so too is the radius. So how is the radius changing is my question. Mr. Haas's example kind of demonstrated to us that the radius is not going to be changing at a constant rate. Go back and look at that again. Let's see if we can come up with a way of determining how fast the radius is changing at different times. Okay? Now, I mentioned at different times. So the first thing we need to zero in on is that we are now talking about rates of change over time. My y value here is square centimeters, and my x, or my independent variable, is time. All right, so what is another word for rate of change in calculus? Yeah, derivative. So I think we're going to be working with derivatives here. So I know that the derivative of area is 2 square centimeters per minute. So let's use some calculus notation here. And I'm going to use Leibniz's notation, so it makes it very clear that my y value is my area, so I'm going to use A, and my independent variable is time, so I'm going to use time. So what we were just told was that the change in area is 2 square centimeters per minute. And what I'm wanting to know is, how would I describe the rate of change in the radius over time? How do you think we could start this? Well, is there any equation from geometry that relates area of a circle with the radius of the circle? Of course there is. We know that area of any circle is given by pi r squared. So I have an equation that relates the area and the radius. Now I want an equation that's going to give me a relationship between the rate of change of the area and the rate of change of the radius. In other words, an equation that gives me a relationship between the derivatives of area and radius. Pause the video and see if you have any ideas. Yeah, let's take the derivative of both sides. But as we take the derivative, we have to ask ourselves, well, what is my independent variable here? My independent variable is time. So I need to take the derivative of each piece with respect to time. Implicit differentiation is what I'm talking about. Time is my independent variable. So let's see how this goes. What's the derivative of A? Well, you can think of it as having an invisible coefficient of 1. So if this were a y, what's the derivative of y? Y prime, right? So the derivative of A is going to be A prime. And I'm into Leibniz's notation today, so I'm going to, instead of saying y, A prime, I'm going to say dA dt. All right. What's the derivative of pi r squared with respect to time? Well, pi is just a constant. R squared, the derivative of r squared, power rule, that's going to be 2 pi r. And then the chain rule times the derivative of r. Well, what's the derivative of r? R prime. Or in Leibniz notation, dr dt. And there, just like that, we have a relationship between the rates of change of the area and the rates of change of the radius. Let's substitute in the specific information we have. Well, I know that dA dt is constant, it's 2. So now I'm just going to do a little algebra. Divide by 2 pi r, and we can clean that up a little bit. There is an expression for the rate of change of the radius over time, right there. So let's say we wanted to figure out how fast the radius was changing when radius was 1 centimeter. Well, we would plug in a 1, and we would say that is going to be 1 over pi centimeters per minute. Okay? How about if we want to figure out how fast the radius is changing when the radius is 10 centimeters? Well, that's going to be 1 over 10 pi centimeters per minute. So 1 over pi, well, that's like 1/3 centimeter per minute, okay, compared to 1 over 31 something, right? So clearly the radius is moving much faster when the circle is smaller. When the puddle is big, the radius is changing much less quickly. So this, my friends, is how we are going to approach related rates problems. I'd like to, 1, draw a picture and determine the variables. So my variables here were area and radius. 2, write an equation that gives you a relationship between the variables. 3, take the derivative with respect to time, because time is your independent variable. And 4, substitute in any values. So I might ask, how fast is the radius of this petal growing when the radius is 1 centimeter? How fast is the petal growing when the radius is 10 centimeters? And so on and so forth. Okay. These are fun problems. They can get complicated, but I think they're fun.